Nuclear power holds a terrifying reputation, yet it remains our most energy-dense and carbon-free power source, capable of cleanly lighting entire cities for decades. The modern architectural answer to that fear is the Westinghouse AP1000. It is a reactor built entirely around harnessing and containing the chaos, safely locked inside this tiny ceramic cylinder. Just look closely at the scale here. These are enriched uranium-235 pellets. To power a massive facility, you stack about 430 of these little pieces end-to-end inside completely sealed welded metal rods. Inside that metal rod, the uranium-235 nucleus sits in a highly unstable state. If a free-floating neutron happens to bump into it, the nucleus absorbs it, deforms, and forcefully fractures into entirely different elements, like strontium and krypton. That split converts a tiny amount of mass directly into immense heat. Nature prefers stability, so when that atom breaks apart, it ejects 2 or 3 free, unused neutrons. Those newly freed particles fly outward through the core, striking other uranium atoms, triggering more fractures, and causing the heat to multiply exponentially. Constructing a plant like the AP1000 is a massive exercise in restraint. Every component is engineered to cage an atomic chain reaction that would otherwise melt straight through the floor. To keep that reaction from spiraling out of control, the core requires a highly tuned environment. The water circulating through the reactor is mixed with boric acid. Boron is an excellent neutron absorber. By adjusting its concentration in the water, operators intercept just enough fast-moving neutrons to keep the fission rate perfectly stable. When operators need to hit the brakes, they use control rods. These are made of a silver alloy and act like powerful vacuums for neutrons. Lower them into the empty spaces of the fuel grid, and they absorb enough flying particles to mute or completely kill the reaction. The core is an extreme environment, so these control rods are manipulated through sealed walls using a clever mechanical linkage. They are held suspended above the reactor entirely by the magnetic fields of heavy copper electromagnets. This provides the ultimate mechanical failsafe. If the plant experiences a total blackout, those electromagnets instantly die. Without power, spring-loaded latches naturally pop open, and gravity pulls the heavy rods straight down into the core, shutting off all fission in 2.5 seconds. The entire reactor operates in a state of constant, deliberate resistance. The moment human intervention or electrical power fails, the laws of physics force the system to default to off. Even with the reaction under control, we still have to extract all that intense heat. The water flowing directly through the nuclear core reaches over 600 degrees Fahrenheit, and it is highly radioactive. It can never be allowed to leave the sealed primary system. Instead, that radioactive water is pumped into a massive heat exchanger called the steam generator. Here, it rushes through a dense bundle of over 10,000 highly engineered U-shaped metal tubes. These thin walls act as a strict physical quarantine barrier. A completely separate feed of clean water is pumped in to surround those tubes. As the clean water washes over the scorching metal, it absorbs the heat and violently boils into steam, while radioactive water stays securely trapped inside. Water droplets hitting downstream machinery act like little rocks, so that rising vapor must be purified. It's forced through spiral swirling vanes and banks of zigzagged metal plates, stripping away the heavy moisture to ensure only perfectly dry, clean steam exits the building. By maintaining 2 strictly separate loops of water, the plant can harvest the immense thermal wealth of the nuclear core while entirely isolating its lethal radioactive threat. But the true test of a nuclear plant is what happens when everything goes wrong. Imagine a total station blackout. Off-site power is dead, backup diesel generators fail to start, and human operators cannot intervene. Even after the control rods drop and the chain reaction stops, the residual heat locked in the core remains immense. If water isn't continuously flowing to carry that heat away, the fuel can melt through its metal casing. This is where passive safety systems take over. On a loss of power, a series of pre-pressurized and gravity-fed tanks automatically fail open. They force hundreds of thousands of gallons of cold makeup water directly into the reactor, without relying on a single electric pump. As steam builds up and fills the massive containment vessel, the building itself becomes a radiator. An 800,000-gallon water tank permanently sitting on the roof gravity drains directly onto the hot steel dome. That water evaporates into steam, drawing heat away. while natural drafts of cold outside air continuously pull the vapor out through roof vents. This cooling cycle can run entirely on its own for a full 72 hours. To survive the ultimate disaster, modern reactor design stops fighting nature and instead recruits fundamental physics, gravity, pressure, and evaporation, as an unbreakable safety net. Meanwhile, under normal operation, that perfectly clean, pressurized steam travels out of the containment building and into the turbine hall. Here, it violently expands against thousands of intricately machined blades, spinning massive high and low pressure rotors to generate electricity. But extracting this much energy comes with an inevitable consequence. After 18 to 24 months, the usable uranium inside those tiny pellets is spent. The resulting byproducts are highly radioactive, and direct contact with them won't be safe for thousands of years. When it is first removed, the used fuel is literally hot enough to boil water. Robotic cranes transfer the assemblies into a 42-foot-deep spent fuel pool filled with borated water. They have to sit submerged in this glowing quarantine zone for about 5 years just to cool down. Once cooled, the fuel enters permanent dry storage. The assemblies are sealed into metal canisters, pumped entirely free of air, pressurized with helium to prevent rust, and then encased in thick, heavily shielded concrete casks. The physical footprint of this byproduct is remarkably small. 60 years of providing continuous, high-yield power to nearly 1 million homes results in only about 150 of these massive casks, fitting entirely on a single concrete pad. Nuclear power forces a stark bargain. It demands meticulous engineering, flawless execution, and a millennia-long commitment to managing toxic waste. But in return, it offers the closest thing we have to limitless, carbon-free energy.